All right, so we'll start at the beginning of the quarter when we talked about fluid flow and Bernoulli's equation, continuity, all that stuff. Um, so first thing we started with, remember we're talking about energy density for these problems. So it's not joules, it is joules per centimeter cubed. Or I mean, it could be kilojoules per meter, like whatever the units are, it's energy over volume. And the reason we did that is because that tells us about the behavior of the system. We want to know the energy density of the fluid. We don't care how big the system is necessarily. If we have a pipe that's the same dimensions, but or like the same cross-sectional area and like no friction, no height difference or anything like that, one that's 5 feet long versus one that's 10 feet long will act the same, right? The fluid's going to flow through it in the same way with the same energy density characteristics, so we would want to describe them as having an identical measurable quantity, this energy density. We don't really care that even though like the 10-foot pipe is going to have twice the amount of energy in it, right? Because there's twice the amount of liquid just because it's longer, because the behavior is not any different. So takeaway, energy density is what we're dealing with now. Another thing also, we have a lot of deltas in this. So, I mean, we'll see it in the next few slides, but we're looking at the change throughout a fluid circuit. And when we say change, we're talking about change in physical distance, change between point A and point B. There's no change in time because these are steady state fluid circuits. Steady state just meaning there's no change in time. So my system is not static. There is fluid flowing through it, but it looks the same at time 1, time 2, time 3, whatever. So in a steady state fluid system, current is conserved. What that means is that my current here is my current here, is my current here, is my current here, is my current there. Current is the same everywhere. Current is calculated by multiplying the cross-sectional area by the speed that the fluid is moving. We don't need to do the full derivation of it, but basically you can derive that from just saying the volume of fluid in this like cylindrical piece here, moving at a certain amount of time and like through a certain point. Anyway, I did that in lecture, but you're not responsible for it from the exam. What you are responsible for is that current is cross-sectional area times speed, or I equals AV, at every point in the fluid circuit. So I1 equals I2, or A1V1 equals A2V2. And that's true anywhere within a single fluid circuit. That's another key. Single steady-state system or single fluid circuit, because there's no continuity rule between two different fluid circuits, right? If I have one over here, one over there, there's no continuity rule between them, but if they're connected, part of the same circuit, then we do have this continuity. The same thing is true if I alter a fluid circuit. So I have one fluid circuit, we solve everything, know how the whole system works, but then I add a pump somewhere in it. That is going to change my fluid circuit. So we're no longer bound by that, like the current that was there before we added the pump to the current that was there after. Those two can be different. Each individual one of those, though, the circuit with or without the pump, will obey this conservation of current. So super important, conservation of current in a steady state system. So let's talk about our energy density systems that affect or that change as we travel throughout a fluid circuit. So first we have potential energy density, very similar to what we saw in 7a and what we see now a lot throughout the quarter, but it's just gravitational potential energy. The higher up you are, the higher you can fall. And so we have our potential energy, again, density is equal to rho GH. Density times gravitational constant times height. And the reason we have rho here instead of m, just the mass like we had in 7a, is again density. So we just switch out kilograms for kilograms per meter cubed, or whatever units we're using. So yeah, rho GH. And a simple example in just this one is both a steady state fluid system and a static one. Here there's no flow, right? This is just a cup of water. If we want to find the difference in pressure between points 3 and point 1, we would just have our delta P term and our rho GH, the H being the height difference between the two of those. The rho there would just be the density of water, and G is gravity. We use potential energy density as a pressure gauge, right? Remember we had this system, this type of setup with the standpipe a lot when we did Bernoulli equations. So when you put a standpipe, so if we ignore the pipe first, we just have a pipe with fluid flowing through it. It has some flow rate I, and there's, well, if we ignore friction, ignore everything else, this is kind of an uninteresting system, right? But there's some pressure in this bottom tube here. The water flowing through has some pressure, some energy density. If we put a standpipe on top, that pressure is going to cause the water to flow up through the tube. But it's not going to flow up forever. It's going to stop at a certain point. When is it going to stop? Well, when the pressure reaches 1 atm. The reason it decreases is because the potential energy density is decreasing as it flows up. Right? So if we write out our Bernoulli equation for this system here, I don't know why this text is so small, but this is just delta P plus delta PE over volume. And so if delta PE over volume goes up, my delta P must, or my pressure must go down, right? We're spending some of that pressure on potential energy, building up the potential energy, and then once we run out of pressure, we stop increasing our potential energy, or when it's in equilibrium with the atmospheric pressure outside. So that's a very important thing to remember too. Whenever we have our fluid exposed to the air, you know at that point that the pressure is atmospheric pressure. So anywhere in a fluid circuit where the fluid is in contact with air, it's at atmospheric pressure, 1 atm, and then you can solve, away from there to get pressure at other points in the fluid circuit, which in this one is just finding the pressure difference between our PATM and down at the pipe. A couple assumptions we make here are that there's no pressure difference within this bottom pipe here, right? So we'll say the pressure in the middle of the pipe is the same at the top and the bottom, just because its height is small compared to the height difference in a standpipe or outside of it. Another important thing, why this exposed fluid is at atmospheric pressure, it's because they're in contact. If one system is in contact with another, or in this case the water in the standpipe is in contact with air, if the pressures were not equal, that point of contact would move, right? If left and right are in contact, right has greater pressure, it will push the one to the left until they're at equilibrium. So because this line is not moving, we know that they are in equilibrium and at the same pressure. They're pushing equal and opposite on each other. It's like a little flash forward to something we looked at later in the quarter. Right, so here we just find that our pressure at point 1, which is right at the top and like in this bottom tube, is just atmospheric pressure plus the rho GH from the height difference. So it's a higher pressure, and that's a good just kind of intuitive check when you're doing fluid systems. If we dive down deeper, our pressure should increase, right? If you dive underwater, if you feel pressure on your ears, pressure increases. Kinetic energy density. That happens when the area changes, right? So our indicator for potential energy is height difference. So if the pipe goes up or down, or any of the fluid goes up or down, our indicator for kinetic energy density is the area. We know that kinetic energy is calculated as 1/2 rho v squared, or 1/2 rho delta v squared. Again, the rho is just swapped out for the m because we're dealing with energy density. So why do we look at the area if what we care about is the speed? Well, because like we saw from our continuity equation, sorry, I guess my animations on these slides just all showed up on top of each other, but we know our speed is just our current divided by our area, because our current is area times speed. So if we know our current, we can just divide by the area to get the speed of the fluid and get the kinetic energy density. So again, area is the indicator, and that's what's going to tell us if our kinetic energy density is changing, but the real thing that's used to calculate it is speed. but they are intimately related. So what this tells us is that a larger area means that the fluid has a smaller speed and a smaller kinetic energy. So if the area of my pipe goes from small to large, there's a decrease in kinetic energy density. And if the size of my tube goes from large to small, there is an increase in speed and in kinetic energy density. So that's a little backwards. A growing tube makes it go slower, lower energy density. A way to think about that in terms of like continuity, a little more in qualitative terms, is if I have a certain amount of fluid that's flowing through the system at all points, right? That's just conservation of current, that the amount of water passing through this point is the same as the amount of water passing through this point at all times. So if this point, if one of them is more narrow than the other, then the water has to be moving through there quicker in order to get the same amount through, right? If I have two doorways, or I have a doorway and a garage door, and I want to get 3 people through every second, they're going to have to really hustle through the narrow doorway in order to get 3 people through. But the garage door, they can just walk out nice in their own time, side by side, 3 at a time maybe, and they won't have to rush as much. So that's why the expanding, giving bigger area, slows the fluid down, and you get a change in kinetic energy density as a result. Also, feel free to stop me at any point, ask me questions, or something that you want to see in a little more detail. If there's a topic that you have in mind that I just kind of gloss over or miss, please let me know. This is just, again, a selection of slides from my 10 lectures. It's not comprehensive. Okay. All right, so we have potential and kinetic energy density. Now we're left with 2 more, thermal and, as we'll see next, pumps. Thermal energy density is our friction, right? That's our dissipation. When there is resistance, friction, dissipation, any of these key words in a problem, you know that there is thermal energy density. So we can think of that as adding thermal energy density or subtracting, like minus IR dissipation, right? It depends where you put it in the equation, and I'll put this all together at the end, like where we'll see the equation together, but really it's just another way for, we have this amount of pressure, is energy density in the fluid, and we can spend it. We can spend it on potential, we can spend it on kinetic, we can also spend it on thermal energy density. The difference, I guess, is that we can't get it back, right? If you have a tube that goes up, you spend some pressure on potential energy density, right? So your pressure goes down, but then the tube can just go right back down. My potential energy density goes back down, and my pressure goes back up. Same thing with kinetic. Pipe is narrow, goes to wide. Pipe is wide, goes to narrow. That increases my kinetic energy density, lowers my pressure. We can just make it wide again and bring the pressure back and the kinetic energy density back. Thermal energy density, you can't do that, right? If I have a section of pipe that has some resistance, some friction to it, we're going to lose some pressure to thermal energy density, right? It's going to heat up and lose pressure, but then there's nothing we can do to reinvigorate that thermal energy back into the fluid. So that's why we often just take this E thermal over vol and just put it on the other side as a minus IR term, because it's really just subtracting away. The opposite of that is a pump, which adds energy density. So this is just kind of like the opposite of thermal energy dissipation, in that it's something that injects pressure into the system, injects energy density, but there's no, unless you put another pump that's facing the opposite way to take it out, it's just kind of added to the system. So this pressure, potential energy density, and kinetic energy density are changing and exchanging as the fluid flows through the circuit, and then the kind of net addition or subtraction comes from thermal energy dissipation or energy density from pumps, right? Those are the two things that are like adding or subtracting from our system. So you can think of a system without dissipation or without a pump as kind of like a closed system. I don't know if that's super helpful. So let's look at our complete equation now. On the left-hand side, this, we call it our total head. delta P plus delta P over vol plus delta Ke over vol. Again, those are the things that change and exchange as we go through. And then the right-hand side is pump and dissipation. The other important difference to notice between the left and the right sides here is that the left side has deltas and the right does not. The reason being, these are all changes, like we said, evaluated between 2 points, between point A and point B. What's our change? On the right, an E pump or a minus IR happens in between our 2 points, right? We don't care if there's like a pump. Yeah, pumps and dissipation are localized. They're at certain places. I guess dissipation can be spread out, but if it happens between A and B, we care about it, right? And so these are just pressure at B minus pressure at A. Potential energy density at B minus potential density at A, so on and so forth. These you have to include if a pump or resistance is anywhere in between your points A and B, right? Anywhere in between. And yeah, I mean, just to show you why that can't be true for pressure or something, we don't care what happens in between for pressure, potential energy density, and kinetic energy density, only the endpoints. Because, like I said before, I mean, this is similar to when I was saying you can get it back, right? For potential energy density, here's my point A, here's my point B. They're at the same height, right? In between, the pipe could go up a foot and then back down, but my potential energy difference is still 0 between A and B. It doesn't matter that the pipe went up and down in the middle, right? Because whatever it gave away, it got back, right? So the pressures can still be the same. Same thing with kinetic energy density. It can get narrow and wide, narrow and wide, narrow and wide. All it matters is what was the initial and what was the final. That's not true for pump and dissipation. Yeah. And then beyond that, it's just solving problems where you have to first identify these important setups. What's my point A? What's my point B? Which of these terms differ? Like pressure, well, pressure you can't just read off unless you have some sort of pressure gauge. But does my potential energy change? Does my kinetic energy change between these 2 points? And then is there a pump? Is there dissipation between them? And then solving. But if you can identify what your point A and point B should be and find what's unknown and what's not, going from there is pretty straightforward. However, getting to that point might be a little tricky. Again, you have to make use of where do I know the pressure? Do I have a standpipe somewhere? Is there a hole in the pipe that leaves it open to the atmosphere? Is there, so on and so forth. Okay, so that's my little review for Bernoulli and fluid flow. Any questions or specific things about this topic that you want to see before we move on to circuits? What did you say? Oh, the slides. I have not put this on Canvas yet. I will. These are just slides from previous lectures. So I just assembled them together, but I'll post this whole thing on Canvas after it under just like review session. Okay, so let's move on to circuits. Electric circuits. We saw they're very similar in a lot. Do you have a question back there?
So you just mentioned like the area increases, so you that reduce the kinetic energy or increase the kinetic energy.
Does what increase or decrease?
The surface area A increases. So is that reduce kinetic energy?
If A increases, kinetic energy density reduces because the speed goes down. And we can find that just from our continuity or our kind of definition of current, which is current is area times speed. So my current stays the same. So if my area goes up, my speed goes down, or my kinetic energy goes down. And the opposite, if the area goes up, if the area goes down, my speed and my kinetic energy density must go up. All right, so electric circuits. We took a little detour in lecture and in DL when we talked about like linear transport in general, right? We said we did fluid flow, and then we said, oh, this can work for temperature differences, then heat flow. This can work for diffusion. that is not going to be on the final. We're just going to do fluid circuits and electric circuits, so you're not responsible for this like general linear transport.
So what would be the exams? Sorry.
Fluid flow,
Flow.
so like Bernoulli's equation continuity, and then circuits, so resistors, capacitors, batteries, all that stuff, but nothing about temperature and heat flow, nothing about diffusion. Like we did some stuff with like just linear transport in general. All of these things are linear transport models. That just means like I have this one quantity, whether it's a delta P, like a change in pressure, change in temperature, change in concentration, change in voltage, whatever, and that difference drives a current from one place to the other. That's our like zoomed out general way to view these physical phenomena. You don't have to do that. You just need the zoomed in fluid flow, the Bernoulli's equation and continuity equation that I had on the previous slide, and then what I'm about to talk about in the context of circuits. So for circuits, that kind of link from Bernoulli to circuits was that now our energy density, instead of being energy per volume, it is energy per charge. Right? We're not talking about a volume of water or fluid that's carrying energy. We're talking about each electron or proton, whatever unit of charge, is carrying some amount of energy throughout the circuit. And that unit, that charge, so the units are now charged. Everywhere where you would have volume, just sub it out for coulombs or charge. We don't really use coulombs all that much in most of our problems, but the energy density now is voltage, which is joules per coulomb. And the units for our current are coulombs per second. Instead of meters cubed per second or volume per second of fluid, it's amount of charge flowing through per second. And so we get something very similar, except we write it as a loop rule. The loop rule is kind of like our Bernoulli's equation in a way for fluid circuits, for electric circuits, except now the key word is loop. So circuits. We did a little bit with fluid circuits where we went all the way in a closed loop for fluids. We're not going to do that on the final. You'll have just, fluid flow and then electric circuits. But the nice part about circuits is since we go in a complete circle, our delta V, or our change in voltage, ends up being 0. Right? If I start at one point and I find the energy density changes as I go around a whole circuit and come back to that one point, I better have exactly what I started with. Otherwise, I could just go around the loop and infinitely increase my energy or something, which is not possible. So anyway, I think I have more slides about this. I'm kind of skipping ahead from this. But electric fluid flow around a circuit, remember charge or current flows from the positive side, so the long side of the battery, to the negative side of the battery, the short side. That is backwards from what happens in real life. In real life, electrons are what's going through the circuit, so the charge that's moving through is negative charges, and they flow from this negative side to the positive side. But for whatever reason in physics, current is the flow of positive charge. So it's just flipped. So current leaves the positive side, goes through the circuit, and comes back in the negative side. Like I said, voltage is our new energy density, joules per coulomb, or energy per charge. Batteries, for our current, electrons gain and lose energy density as they flow through a circuit, so energy density being voltage. And we also, this delta, I didn't mention this before, but our delta, just like for fluid systems, is spatial. Right? Until we get to capacitors, until we get to exponential change, everything is steady state, and so there is no change in time. We just want to know what's my voltage here, what's my voltage there, what's the difference between those 2 points. And again, if we go in a loop, that change needs to be 0 because my start and my end point are the exact same. Okay, so let's talk about the components of a circuit. We started off with just batteries and resistors. Right? Batteries have some positive delta V across them, so going from minus to plus, it's kind of intuitive, right? We jump from minus to plus, we get we add voltage, and that is represented by this letter epsilon, this curly E. That's just, do I have a 5-volt battery? Do I have a 10-volt battery? Whatever it is, that's how much energy each charge will gain when it's pumped through the battery. Then we go around the circuit, again, leaving from the positive side of the battery, and then we go through a resistor. The delta V, or the change in voltage across a resistor, is negative, and it's negative IR, just like very similar we had with dissipation in fluid circuits, but the charges lose energy density as they go through the resistor. So batteries pump energy density in, resistors dissipate it out, and that's how when we go in a complete circle, we have a positive addition from the battery, negative from the resistor, and we get back to 0. And it has to be that. So in a simple circuit where we just had like a battery and a resistor, the amount of voltage, the voltage drop across the resistor is the equal and opposite to the voltage drop or voltage gain across the battery, right? If I have a 20-volt battery, then my resistor will have a negative 20-volt voltage change across it. If I have a 5-volt battery, negative 5 volts across the resistor, because when I go around in a loop, I have to get back to 0. So this next slide demonstrates this a little bit. In a circuit, I write down my loop rule, which is just my delta V loop going from one point, and that's any point in a circuit all the way around back to that same point, has to be 0. That would be like saying that voltage at point 4 minus voltage at point 4 is obviously 0. And then to do that, I go around and add up all the elements in the circuit, their voltage changes that I encounter as I go through. So starting at point 4, I go across the battery, and I get this positive epsilon, right? The battery pumps some voltage into this charge. So now we have epsilon. I put that in my loop rule. And then I go around. It's written out here that the difference between, like, as I go from 1 to 2 is 0, because this is just a wire, which we'll assume has 0 resistance. So if there's nothing in between these 2 points, there's going to be no voltage change. Then I hit my resistor. So going from 2 to 3, I have the voltage drop across the resistor, which, like we said, is minus IR. And then from 3 to 4, again, there's nothing, and I'm back to my start point. So going through that whole loop, I accumulated a plus epsilon and a minus IR. And we know that that's equal to 0, which allows me to find this very simple relationship or solve for the current, right? And that's if I had my epsilon and my R, I could solve for the current in this circuit. Or if I was told what the current is and the epsilon of the battery, I could solve for R. Whatever we had, I just chose to solve for current here. But once we do our loop rule, we get how all these things in the circuit need to behave together, and that's how we can solve for the circuit behavior. Not all circuits, of course, are just one battery and one resistor. We have very often resistors combined together, many resistors in the circuit. And there's 2 ways that they can be combined, either in series, which is, as the name suggests, just one after the other, in which case they just add, right? If I have a resistor R1 and a resistor R2, then I'll lose some voltage due to R1, and then I'll lose some more voltage due to R2. So their voltage drops just add together, or in other words, their resistances add too. We derived this. You're not responsible for the derivation, but just so you know, we derived this equivalent resistance for 2 resistors in series is just adding them together by doing the loop rule. So this is a result of the loop rule. Key takeaways about resistors in series, not just that their equivalent resistance is the sum of their resistances, but also that the current through them is the same, right? And that should be obvious from our continuity equation, which says that our current is conserved in the circuit, right? Our total current. There's nowhere else for the current to go, right? If I have 5 electrons per second going through this first resistor, then I better have 5 electrons per second going through the second one as well, because everything that goes through 1 has to go through 2. There's nowhere for them to go elsewhere, or for more to be added in here. So if we didn't have that continuity, then there'd be like a buildup or a dissipation of charge, which does not happen. Their voltage drops do not have to be equal, right? In fact, they're not unless the 2 resistors are equal. So you could have, if R1 was much bigger than R2, you'd have a bigger voltage drop across R1 than across R2. because the voltage drop is minus IR, and so if the I is the same, then the voltage drop just scales with that resistance. The other way two or more resistors can be combined is in parallel. That makes it a little more interesting. That's when we have multiple branches, multiple options for a charge that's going around the circuit to make. So a charge leaving this battery could either go through R1, come back, make a loop, or go through R2, come back, make a loop. It cannot go through both, right? So the loop rule also, it's a little more work, but we can use the loop rule to also derive this relationship for how these two, R1 and R2 combined in parallel, combine together, which we get this 1 over Req is 1 over R1 plus 1 over R2. Really important to remember that 1 over R1 plus 1 over R2 equals 1 over Req. I still make this mistake today where I just solve 1 over R1 plus 1 over R2, and that's my answer. But no, you have to do 1 over whatever that is in order to get your R equivalent. A good check on these is that your equivalent resistance for any amount of resistors combined in parallel has to be smaller than the smallest resistor. Right? So if I have a 5 ohm resistor, a 10 ohm resistor, and a 20 ohm resistor all combined in parallel, my equivalent resistance is going to be smaller than the smallest one, which was 5. So it will come out to probably like 4 point something. But that's a good check. If you're combining things in parallel, your result must be smaller than the smallest resistance branch. The reason being is you can think about it as just opening up alternative pathways. Right? So if this circuit here was just R1, it's just a battery across R1, there's some resistance, which is R1. But then if I add on R2, the current still has the option to go through R1. It's just now it can also lighten the load on R1 a little bit and go through R2. So it will make it a little bit easier. Even if R2 is a really big resistor, it might not have as big of a change, but if R2 is anything, if it can allow some charge to go through, it will make it easier for charge to get around and the equivalent resistance will drop. So combining things in series increases the resistance, combining them in parallel decreases the equivalent resistance. Important things to note about parallel resistors is that the current is not equal, right? In fact, the current is still conserved. We still have that. But now that we have these junctions, we have to factor in that it splits up, right? So we have some I total leaving the battery, but then that splits into one current that goes through R1 and one current that goes through R2. Those two things, I1 and I2, have to add to I total because we still have some total amount of current. And then when they come back together, they'll form I total again. But once they're in those two separate branches, they will be, there's nothing that says they have to be the same. Unless, of course, they're the same resistance, in which case they'll behave similarly. And we know, I mean, you have to do some more math to know exactly what they are, but the larger current will go with the smaller resistor, right? Whichever way is easiest, the charge wants to go through, and so more of it will. Some will still go through every resistor, but whichever one's easiest, more of the charge will go through it. So it will have the higher current. I don't think I have a slide on this, but there's also like shorting a circuit. That's when if I add another branch that has no resistor, that's just a wire, then it will act like these resistors just weren't there. That makes it infinitely easy for the charge to go elsewhere. And so none of it will go through the resistors. So when we say shorting a resistor, shorting a light bulb or something, that just means adding a resistanceless wire in parallel with it. And then it's like it wasn't there. It decreases the equivalent resistance to 0. So if it was a light bulb and you shorted it, it would just turn off. There would be no current lighting it up. What resistors in parallel do share, they don't share current. What they share is a voltage drop. Why? Because they have the same starting and end points, right? The voltage at the beginning, at the first junction, the voltage at the first junction and the voltage at the second junction are common between each one. I mean, that's kind of implied in the fact that I call them junctions, but before R1 and before R2, there's nothing that changes the voltage. And then after R1 and R2, there's nothing that changes the voltage. And you have to get the same answer here. Like, you have to have the same answer for both before and after because of that. I can't have two answers for voltage at one point, and so they have to have the same voltage drop. So to sum up, in series, they share a current, they do not share voltage drops, and the resistances add together. In parallel, the inverse of the resistances add together. They do not share a current, but they do share a voltage drop. And the individual currents add up to equal the total current. Finally, we have power dissipation. And I say finally, that's when it comes to batteries and resistors. We haven't talked about capacitors yet. But power dissipation is just energy dissipated over time. So like we said, there is dissipation in these resistors, and we can find the amount of power that is dissipated. So how much energy are we losing per time in these resistors with any of these expressions on the bottom for our P resistor. So you can either multiply current times the voltage drop, or current squared times R, or delta V squared over R. It doesn't matter. These all will give you the exact same answer. One will just be easier. You'll already have two things. If you have I and delta V, use this one. If you have I and R, use this one. If you have delta V and R, use this one. But we all know that we have a pretty simple relationship between delta V, I, and R. So if you really wanted to use I squared R, but you only had I and delta V, you could just say, okay, well, I know delta V is minus IR, so I'll just solve for R. You know, it's pretty simple. But this long-looking thing is just one piece of information that's saying the power dissipated in the resistor, and you can't go wrong using any of these. We also have power injected into the circuit by the battery, right? If we're losing power, losing energy from these resistors, they're heating up and dissipating it into the environment, or if it's a light bulb, also it's being dissipated as light, we need to get that energy from somewhere, and that comes from the battery. The power injected or power introduced by the battery is just the current times its epsilon, or its voltage. And of course, the total power added by the battery in the circuit has to equal the total power dissipated by the light bulbs, right? Whatever power we put in, dissipated out. We can't just make more power than the battery has to offer. Any questions on that stuff? So I have one quick, I walked through this in like mathematical detail in lecture, but just as a overarching review of this, we have some complicated circuit with a combination of resistors in series and parallel, and we want to simplify it. In this circuit, where are we going to start? Well, let's see, what if we want to combine R1 with the next thing, like in series? Well, we can't quite do that because R1 is not in series with either like R2 and R3 or with R4 down here. It's in series with this whole parallel branch, right? And the same reason we can't combine either of these branches with R5 because, again, you can't combine things across a junction, right? So we can't do that. We'll have to start with this branch here. Can we just combine R4 with R3 and R2? No, because R4 is not in parallel with either R3 or R2 individually. It's in parallel with them together. So that's where we have to start. The only thing we can easily combine first is combining R2 and R3 in series because they're right next to each other, so we can just turn them into R23, a single resistor, which is just the sum of their resistances. Okay, now same argument, we can't combine R1 or R5 with this parallel branch yet, so we'll have to combine R2 and R23 with R4. And now we can do that because it's just one resistor in parallel with another. So we have that inverse equation relationship for REQ, and we get that the R234 equivalent is now 3 ohms. Let's check that. Is that smaller than 5, which is the smallest resistor that was in that parallel set? Yes, it is. So that's just a good check for us. And now we're just left with 3 resistors, R1, R234, and R5, all in series, which we know we can just add them together, and we get some R equivalent for the whole circuit. And then we can go solve its behavior. So if we wanted to find the behavior of this circuit, now we just have a simple delta V equals minus IR, right? We know delta V, we know R, so we can find the current. Then I could go back up to this more generalized three resistor circuit and use that current to find the voltage drops across each of these resistors with just minus IR. Right now I know the current, I have the resistances. Then if I wanted to take another step back and look at this parallel branch, now I know the voltage drop across each of these, right, which is the same, and it's the same as the one for the equivalent resistance, right, because all of these we just have to get from this voltage before to this voltage after, so it has to be true for either branch. So for each of these, now I have a new voltage drop and a resistance, so I can find the way the current splits in between them, so on and so forth. Then I can get the voltage drops for R2 and R3. So lots can be done here. But in the end, when you're doing these circuit problems, the order of operations is to simplify down to a battery and a resistor, and then go back, trace your steps back to whatever level the question is asking you for an answer in. Questions on battery resistor circuits before I move on to exponentials and capacitors? Yeah.
So this one will be asking us to find the battery, power battery.
I could ask it. I mean, there's no question posed here. But if I wanted to find the power dissipated by the battery, or the power introduced by the battery, I would have to go all the way to this final step, because I want to find the current in the circuit. And then once I found the current here, my total current is going to be the same in all of these, right? That's the whole point in finding an equivalent resistor. It's that the battery feels the same resistance in this circuit, as this circuit, as this circuit, as this circuit. So the total current coming out of the battery does not change. So if I got to this step, find my total current, then just that I times epsilon, which I have, would be my power introduced by the battery. If I want to find the power dissipated in each one of these individual resistors, I'd have to work backwards to the steps where I could find the current in each one. Or, it could be something like you could just ask for the current in R2 or R3, or the voltage drop, something like that. But yeah, the main work is getting to here, and then there's maybe an extra step or two in just getting the exact form of the answer I want. Like, the simplest thing would maybe be to get, like, I would find the current in this branch first, and then I would have to go, okay, I want the voltage drop across R2, so I have to do the current times R2, and then I want the power dissipated, something like that. I'm just making stuff up, but the meat of the work is simplifying and going back out. And if you can do this, you should get at least pretty good partial credit, even if you're lost as far as how to proceed in the opposite direction. All right, let's move on to exponential decay. So I'm going to take a break from talking explicitly about circuits for a sec, and then we'll relate it to introducing capacitors in a circuit. So exponential decay has this form here, where we have some y, so some value is equal to its initial value, so here y naught, that's just y at initial time equals 0, is equal to e to the negative t over tau. So it's e raised to a negative power, and that creates this chart that looks like this value y decaying from our initial value, from y naught, down at a slower and slower rate until it asymptotically approaches 0. So after a long amount of time, this decays to 0. And not just the value is decaying, right? Sure, it's decaying from y naught down to 0, but also the rate of change is decaying here. We have a steep slope to start with, and then that slope gets shallower and shallower and shallower until the slope is also asymptotically approaching 0. And that's a better general way to describe exponential decay, is that the rate of change is decaying. Because, as we'll see in a bit, we also have exponential decay where the value of the thing grows. Like y might start at 0 and grow, but the slope is still decaying, and it asymptotically approaches a constant value instead of decaying downward. but we'll get there. The keys to, or like key points on these charts are, if we plug in time 0, then we get y0 times e to the negative 0, or just e to the 0, which is 1. So as we wanted, that's why we called it y0. Y of 0, like y at time 0, our initial time is just this value, y0. That's what we're starting at, decaying from or decaying to. Also, we can plug in t equals tau. We'll find exactly what this tau is in a specific context of a capacitor resistor circuit, but for now it's just the time constant. And what it tells us is some characteristic time, like how long our decay takes. Let's see what characteristic time it is. If we plug in tau for the time, so t equals tau, we get e to the negative tau over tau, or e to the negative 1, which is just 1 over e. So y of tau, y of our time constant, gives us our initial value divided by e, which is around 1/3 of its initial value. So that tells us it's a standardized way of describing how long this decay takes. I couldn't just place a number on it, like when is it done, because mathematically it's never quite done, right? It's asymptotically approaching 0. For our purposes, it will reach 0, like eventually, like the last atom will go, but this is just a model, but this equation never truly produces 0. So we need some intermediate value to describe generally how long it takes, and the way we do that is by saying, how long does it take to get from our initial value to that value divided by e, or about 1/3. The reason we use 1 over e and not just a half or something like that is just because, well, it's a clean way to take a value from an exponential, right? We're raising e to a certain power, so it's easier to just, when the exponential equals e to the negative 1, we can get when it equals a half. It's called the half-life, which you have an equation for, but it's just a little messier because we have to get it e to the negative what gives us 1/2, which is just kind of annoying. It's like a much less neat number. But anyway, you have the relationship for those in your equation sheet. It just involves a natural log of 2. But the half-life and the time constant are communicating a very similar thing, which is just like roughly how long, like what is the time scale on which my system evolves, right? So if I have a really slow decaying system, it's going to have a large time constant. If I have a really quick decaying system, it'll have a small time constant. And it gives us a way to gauge that. And it also is an important part on our charts that gives us kind of this transition between a steep slope and a shallower slope. And then if we plug in a much bigger value for time, so a huge time, we get e to the negative huge number, which is essentially 0. It goes to 0. Again, asymptotically, it never truly reaches 0 until you go to like infinity, which is also like a very unrigorous way of describing it. But as you can see, once time gets past a few time constants, we're essentially at 0. So the slope rate of change is what we're looking at again. Larger slope earlier on, and then the slope decays away. So you should really think exponential decay is decay of the slope, decay of the rate of change. So what is this time constant? Like we said, it's the characteristic time, but where does it come from? Well, it's just related to the physical properties of our circuit. So I give examples for like if we had fluid circuits and stuff too, but really it comes from like in an electric circuit, what's the capacitance of our capacitor? Like how much charge can it hold? What's the resistor's value? Like how much is this resistor impeding the flow of current? Those things, the actual physical properties of the system, tell us, is this going to decay quickly or slowly? So again, just another restatement of the things I said out loud, but we transition from early times before tau to late times after tau. It gets shallower and shallower, the slope decreases towards 0. So how do we fit in our idea? Well, I guess this is kind of both what is a capacitor and how does it fit in? Why are we talking about exponential decay? A capacitor is a circuit element where we just have two neutral plates to start with. Neutral meaning there's an equal amount of positive and negative charge, right? So they're not attracted to each other, they're not repulsive, they just don't care about each other. But then we put a battery in between them, and it starts pumping charge, as we know batteries do, from one side to the other. So it's going to pull a positive charge from one side and put it onto the other, which gets rid of a negative charge. So over time, the capacitor charges up or develops this charge, this net charge difference, where one side is positive and one side is negative. And over time, it becomes more difficult to do that, right? Because on these plates, the charges want to repel each other. So this is all happy, they're neutral, nothing bad. But once I start accumulating an excess of positive charge on one side or negative charge on the other, it gets crowded. Right now, the charges are like, there's too many positive charges here, they're all repelling each other. It gets harder and harder to shove more charges on there. And we're limited by how strong our battery is. So eventually, the repulsion from these charges is going to be so strong that the battery can't push anymore, and the circuit will stop evolving. Right? So that's where we get this exponential decay, this decay of the rate of change, is that at first it moves really quickly, it's easy, the battery's just pumping charge from one side to the other, but over time it gets more and more difficult to do so, and it slows down. And that rate of change, that slowing down, is what we're looking at and tracking with an exponential. So if we look at capacitors a little more mathematically, the voltage difference that is applied to them from this battery is related to the charge that builds up and the capacitance. So this is just one equation reorganized, so we could say the charge that builds up on the capacitor is equal to the capacitance times the change in voltage, or the voltage difference from one plate to the other in the capacitor is equal to the charge divided by the capacitance. Either way, yeah, that's the same equation, just rearranged. But really the capacitance is a measure of how much charge can a capacitor hold given a certain voltage. Right, so I have some capacitor, and if it's really big, it's not going to be so hard to put a lot of charge on it. Right, the reason it becomes difficult is because it gets crowded and the charges repel each other. But if there's lots of space, it's not so hard to do so. And so even a weak battery can put a lot of charge on it. But if I had a really small capacitor, there's not a lot of space on it. And so the same battery is not going to be able to put as much charge on there because they'll be repelling each other more, and that battery won't be able to do as much. So there's that kind of three-way relationship between my capacitance, which is how much can the capacitor hold, and the charge that's on it, and the voltage difference between the two. The other thing that affects capacitance, we'll see, is the fact that the capacitors that we see and most practically are used is when we take those two plates that we saw before. Here I just have them on opposite sides. This still works as a capacitor, but we just bend them toward each other. And they're still not connected, but they're close to each other. This does two things. One, it makes a prettier circuit diagram, but also now the plates are actually attracting each other a little bit. So these positive charges, yes, they are repelling each other. They don't want to be on this plate. But that's helped a little bit by the fact that there's a bunch of negative charge just across the pond, just across the gap from them that they are attracted to. So you increase the capacitance of a capacitor by bringing those plates closer together. So you can increase capacitance by either making the capacitor just bigger, giving more space for charges to go on there, making them not repel each other as much, or by bringing them closer together and introducing this attraction to the other one, making them want to stay a little bit in addition to being repelled. So that's the physical picture of what's going on in the capacitor. And now let's, and I guess also introducing them into our loop rule. We haven't talked about this evolving over time, but just a snapshot of it at any given point. We still have our battery, so going our loop rule, let's say starting right to the left of the battery, we get a plus epsilon from a battery. And then we go around our circuit. Now there's a charged capacitor. We know how to find its voltage drop based on the charge on it and its capacitance, right? So now I just have some voltage change across here, which is minus Q over C, sorry. And then same through a resistor, we have our minus IR, and now our loop rule is, very similar to the other one, except now we have this extra component, this extra voltage change, which here is minus QC. Right, but that's not true. I mean, it is true at all times, but this is not a dynamic picture, right? This is just the loop rule at a snapshot. This is the amount of charge on the capacitor. This is the voltage change across the capacitor at a given point. But we know this changes over time, right? The charge starts at 0 maybe and builds up to something. So this Q is changing in time, and we are interested in figuring out how that happens. So let's start at time equals 0. Let's say we have an uncharged capacitor, so it's neutral, right? There's no net charge on either plate, and we close the circuit. This circuit with just the battery and a resistor. When we first start, well, mathematically, there's no charge on here, right? So that Q over C is just 0. There's no voltage change across here. So the capacitor is basically not felt by the battery, right? It can just freely function like it would if the capacitor wasn't there because there's no charges repelling each other on the capacitor plates. So the loop rule at this point is still just our epsilon, nothing from the capacitor minus IR. This is just like a circuit with a battery and a resistor at time equals 0 when it's first closed. Quick aside, the reason current can still flow, like right, if we just had a circuit with a break in it, no current would flow. But capacitors act as a reservoir of charge. What that means, like if I just had 2 wires, there's nowhere to take charge from and move it somewhere else. But since I have these big metal plates, they're full of charge. The net is 0, but there are tons of positive and negative charges on these plates that I can pull from and create a charge difference. If I just have the tips of 2 wires, there's nowhere to pull from, and so I can't create any current flow. Anyway, that's time equals 0. No charge, no current. Current flow is as high as it will go. It's unimpeded by the capacitor. But after some amount of time, so some time greater than 0, some charge has built up on this capacitor. So qualitatively, the way to see that is now it's a little bit more difficult for the battery to pump current through this circuit because it's being opposed by the charges repelling each other on these plates. This plate now has some negative charge. It makes it harder to put more on there. This plate has some positive charge. It makes it harder to put more positive charge on there. And so the current reduces, right? It becomes more difficult for this battery to push, and so the current goes down. We can see that mathematically by now there's a voltage drop across the capacitor, right? So now there is some Q built up, so the Q over C is non-zero, and we introduce this term, and that's going to reduce our current. Another thing we can see, like how this voltage drop is seen as negative, well, we get a voltage increase across the battery when we go from the minus side to the plus side, right? Going from minus to plus, we get a plus epsilon. Let's look at what's happening when we're going from the one side of the capacitor to the other in the direction of our current. So going, in this case, clockwise through the capacitor, we're going from our plus side to our minus, right? So it's flipped the opposite, like the 2 sides are flipped opposite the battery, right? So the battery, we're getting a voltage increase, but the capacitor, we're getting a voltage decrease because we're going positive to negative. So that's another way we can see why this voltage drop, why the change is negative across the capacitor. All right, so let's go even further on. Let's let this evolve for a really long time, many time constants. So I say t is much greater than 0, but maybe it'd be more accurate to say t is much greater than tau, right? That all that matters is that we've waited a long time in comparison to what our time constant is. So if our time constant was 5 seconds, this could be t is 30 seconds or a minute or something like that. But if our tau is 5 minutes, we would need to wait a lot longer, like 30 minutes, 20 minutes, 60 minutes, something like that. But either way, wait until this circuit charges this capacitor completely, and now it's full. Now, it's so difficult to put more charge on this capacitor that the battery is not strong enough to do it, and so current stops. Another way to, so current stops. Now the resistor doesn't come into our loop rule, right? So if we're going through this circuit, we know there's no current, but we'll just go around. We get plus epsilon minus delta VQ, or minus this Q over C from the capacitor, and then our resistor voltage drop, which would be minus R, is not there because I is 0. But it works out, and it just tells us that now our battery voltage increase is equal and opposite our capacitor voltage change, right? I gain epsilon from the battery, lose it jumping across the capacitor. This is just two equal opposed forces, batteries pushing just as hard as the charges on the capacitor, and so no current flows. They're stuck. They've come to equilibrium. What is this here? Maybe I just put those in twice. Okay, so where does the exponential decay come into this? So let's look at the charge building up on this capacitor. So same thing, I just walk through piece by piece. Now I just labeled these times A, B, and C. First closed, partially run through. There's some charge build up on the capacitor, and then after a lot of time, it's full. So this is a plot of the charge on the capacitor over time, right? Initially, it's 0. All the way on the left, time is 0, charge is 0, it's neutral. Then over time, it starts to build up, and it builds up pretty quickly. Because there's not a lot of charge on that capacitor, it's very easy to add more charge to it. However, we know that as more charge builds up, it becomes more and more difficult to add it, and so the rate at which it adds slows down. And that's why we see the rate of change, or the slope of this, decreasing, evening out. And then once we wait a really long time, it evens out essentially to 0. The current goes away. Another way to say that is the charge stops accumulating on the capacitor, and it reaches some maximum value. So this is a good example of why exponential decay is better to think of as a decay of the rate of change, right? Because clearly the charge is not decaying here. The charge is increasing the whole time from 0 up to this maximum value. However, the slope, or the rate of change, is the thing that's decaying to 0. The current would be decaying, right? The current, at this point, when charge is 0, the current is as high as it will be, right? That's when it's easiest for the battery to pump charge around, but then as this goes up and up and up, the current decays away. So the current would look like this flip, starting at some maximum value and decaying exponentially down towards 0. So labeling on here, we'd have A, B, and C, roughly as they are labeled on here. Q increases, but the rate of change of Q decays. And just a note here also, the form of Q, I'll give you, you don't have to memorize the change between the two different ways of writing exponential decay, but since we want this form where it's the rate of change is decaying, but the actual thing, Q, is increasing, we have this 1 minus e to the negative t over tau instead of e to the negative t over tau that's multiplied by the original value. So it's just, you can just take it for granted that this worked. Plug it in. You'll see that if we plug in t equals 0, we get 1 minus 1, which is 0, good. If we plug in t is huge, we get 1 minus 0, which is q naught, which is good. So it does work out. You're not responsible for deriving it, but it does produce this, just like the way the normal e to the minus t over tau produces our decaying value. So now let's look at the current. I said the current would decay. Again, A, B, and C are initial, early, and late times when it's fully charged. Now, initially, we're starting at the highest current we'll ever get to. That's when it's easiest for the battery to push the current around. Then some builds up, and the current decays because it gets a little more difficult to put the charge on the plates. And then once it's fully charged, the battery is no longer strong enough to put any more current on the capacitor, and so the current, which is that charge flowing around the circuit, goes to 0. And like you can see, the form of the exponential for the current is now just back to our e to the negative t over tau, not our 1 minus e to the negative t over tau. But the tau is the same. So just labeling these points. The tau is still the same for the current and for the charge piece, because that's just how fast is this circuit evolving, right? So it's the same circuit where it's just a capacitor charging up. We're just looking at different things. The charge on the capacitor evolving, which is growing, or the current flowing through the circuit, which is increasing. Either one will get from its initial value to this decaying to an asymptote in the same amount of time. So they both have the same time constant, if that makes sense, because they're the same circuit. It's just what the actual values look like can differ depending on what you're looking at in that circuit. So we just looked at a capacitor charging up, but they can also discharge, right? That charge can leave. So I used a battery to fill it up with charge. Then, if I disconnect the battery and connect it just across the resistor, now the charge can flow back. Because imagine what we have. Our final state there is just a capacitor crammed with charge that doesn't want to be there, but it can't leave because the battery is keeping it in check. But if we remove the battery and give the charge a path to leave, then it will. It will leave the capacitor. Because now we don't have the battery, the pressure really, from the battery keeping those charges on there, and so they will flow freely away. Except now, instead of packing more charge on, they will leave in the opposite direction. It will discharge. So now, instead of going from neutral to polarized or charged up, the positive charges will flow back to the negative side and go back to neutral. So in this way, our capacitor almost acts like a battery, because now the capacitor, the charged capacitor, is driving the current. And it's driving it in the opposite way that the battery did. So now going through the resistor, going through the circuit, we go in the direction that the capacitor wants to pump the charge. Across the capacitor, in the new direction of current, now we go from minus to plus. So now we have our voltage change from our capacitor is positive, right? So that's new. When it's charging, the voltage change across the capacitor is negative. And when it's discharging, since it's driving the current in the opposite direction, the voltage change across the capacitor is positive. So it's important to note which direction the current is flowing when you're deciding the sign of Q over C. Anyway, so we flow through the capacitor, we get this plus Q over C, and then resistor, no matter which way you go through it, is a minus IR. It resists the same way in both directions. And so now our new loop rule is just this plus Q over C minus IR. And at time equals 0, so when I first connect it to discharge, I wrote Q max, because that's the most charge this capacitor will ever have. Right? Over time, charge is going to leave, and then this Q is going to reduce, right? Because the second some charge leaves that capacitor, this term will change. The Q will go down. And what that means physically is now the capacitor has emptied a little bit. Now there's more space. The charges don't want to leave as eagerly, and so the whole behavior of the circuit slows down. We can see that directly here, because if this term, this Q over C, decreases, since Q over C minus IR is just 0, we know these two terms have to be equal in magnitude. So if Q over C goes down, IR goes down too. And again, intuitively that just means the capacitor isn't pushing as hard, the charges aren't flying off of it as hard, so there's less current and a smaller voltage drop across the resistor. So we can see that as time increases, charge starts to even out, right? There's less of a charge difference, the current goes down, and until we get to a few time constants or a big, once the circuit has come to equilibrium, all the charge will disappear from the capacitor, and now we're at capacitor discharged. Now there's no voltage change across here, so there's no current, there's no voltage change across the resistor. This is just, there's no flow happening. Everything's neutral, there's no flow of current. So if we look at a plot here, this shows us the voltage change across the capacitor and a resistor. So this is the same circuit, a very similar circuit I've drawn here. It's just kind of rearranged a little, but we have a capacitor that's fully charged, connected across a resistor, and it discharges. So looking at voltage over time of the voltage change across the capacitor and the voltage change across the resistor, we said at our initial time, our capacitor has its maximum charge, its maximum voltage difference, and that means the voltage drop across the resistor has to be equal and opposite to satisfy the loop rule. And then as the capacitor discharges, the charge leaves it, and the voltage change becomes smaller. The voltage change across the resistor also becomes smaller. You can say that's because we're satisfying the loop rule, or because the current goes down. And so if the current goes down, our minus IR term also goes down. And so the sum of these two things stays at 0, right? This plus this is 0, this plus this is 0, this plus this is 0. And of course, as we go far out in time, 0 plus 0 is 0. But yeah, this would be those things plotted out here. And an interesting thing to note, we're not really responsible for this in this class, but that our current is the rate of change of the charge over time. So the current actually tells us about the slope of these lines. Cool thing about exponentials is that the slope is just a constant times the original graph. So it's this thing where the value of something depends on its rate of change, and the rate of change of that depends on its own rate of change, and that goes on infinitely. You're just adding different constants out front. But that's not super important right now. Okay, so any questions before I move on from capacitors and exponential change? I expect you for the exam to be able to explain this type of stuff. You should be able to do loop rules with the capacitor, do stuff like this, analyze its behavior over time. I will not have you do like algebra, much algebra with these. Like from these equations, it will just be like plug in, like what is the value at time equals this? Or if I know my charge is this at time equals that, what is the maximum or final charge, something like that. You won't have to like solve for t based on the charge or something. Yeah. I mean, just at the end of the day, my goal is for you to know the concepts of how circuits work, not how to work with like the math or exponentials. Certainly nothing calculus related.
So if we have to explain the exponential decay of the Q, for example, we have to explain that as the time goes on, the Q increases in the capacitance, right?
If it's charging up.
Charging up.
Yeah, if it's charging up as time goes on, the amount of charge on the capacitor goes up, but the rate of change of that decreases. So the amount, so you can see here, the charge is increasing, but the rate of change of that, the slope, is decreasing.
Rate is decreasing.
Yeah.
Okay.
And that's also, this also is the slope here tells us the current.
Got it.
Other questions about any of this material before we move on? Okay. All right, vectors. How do we represent them? Well, graphically, we have, not just graphically, but just in general, vectors have a length and or magnitude and a direction, right? The magnitude is represented by the length. Just a longer arrow means a larger magnitude, and the direction is just which way the vector is pointing. And to describe that, we would want to, give a length, and then for direction, as we know, there's a bunch of ways we can do it, and we'll talk about components in a sec, but if we're going to give an angle for the direction, we of course need to know what is that an angle from, right? Is that a direction, is that an angle that's like north of east, or north of west, or west of south, or whatever. But if you're going to give an angle, it needs to be very specific. How do we add them together? Well, tip to tail. So graphically, if we're adding vectors, you take one and put the other one starting where that one ended, so on and so forth, and then just connect them from the start to the finish to get your F net. How do we do subtraction? Well, just make it addition, right? Instead of F1 minus F2, we'll do F1 plus negative F2. And to get negative F2, we just flip it around, put the arrow on the other side, and then we just add them like we do any, I didn't show the result of that, but we add them like any other vectors. So then once I have them put tip to tail, I take my start, take my finish, and then just connect them with a new vector. So subtraction and addition are conceptually very much the same thing. Yeah?
Why we didn't talk about non-static
About non-static flow? That's not going to be on the far. So for exponentials, anything non-steady state will only be in the context of capacitors and circuits, where you're not going to have exponential or non-steady state fluid flow. Okay, so how else do we represent them algebraically? Well, we break them up into components, right? So it's great for our intuitive understanding to say a magnitude and a direction, but it's not so helpful when we're actually doing the algebra, mainly because we can treat the x and y components completely separately, right? So it's best to, when we're doing this algebra, break a vector, like f1 here, into its x and its y components. And what that means is, well, how much does this vector extend in the x direction? That'll be our f1x. And then how much does it extend in the y direction? That's our f1y. And then when we add them, we can just do it component by component. So if I have an I have an f1 and an f2, and I want to add them together, I can do it in the x direction and the y direction separately. The f net x is f1x plus f2x. Very similar thing for f net y. And then at the end, I can put them back together. Now I just have my two components of my f net. And they are completely independent. And that will be the story pretty much for everything else, where if you have an x and a y component, or later on like a perpendicular and a parallel component, whatever, if you break a vector up into two perpendicular components, then you can solve the problem completely separately in those two directions. The physics are completely independent. Like if f net is 0 in one direction, then there's going to be no delta p in that direction, and so on and so forth. So that's super helpful. How do we find these components? Well, using trig. In this case, the way I've drawn it, since I have the angle with respect to the x-axis, my fx is going to be f cos theta, and my fy is going to be f sine theta. However, that is not always the case. If I were to give an angle with respect to the y-axis, as I have here, now my fx is f sine theta, and my fy is f cos theta. So it's not a good idea to just memorize x equals this, y equals that. You should be comfortable with finding the components of something based on an angle. And that's especially true when we get to torque and stuff where we need f perpendicular, r perpendicular, because we're not just dealing with x and y. We're dealing with just coordinate systems that are set up based on whatever the problem demands. Doesn't necessarily mean it's harder, but it does mean we have to truly understand what we're talking about when we say the x component, the y component, perpendicular, parallel, based on an angle. Going back, like inversely, if we want to go from having our components to the magnitude and the direction, we can use the Pythagorean theorem and, again, trigonometry. In this case, if I solved for this theta, so if I did inverse tan fy over fx, then I would have to say this is the theta that is north of east, or above the positive x-axis, or something like that, right? If I did inverse tan fx over xy, then I would have to say I would be using this angle here with respect to the positive y-axis, or like east of north, something like that. So very important that along with any direction, you are specific. So what is a force? So we were just talking about forces and adding them as vectors. It's a vector quantity with a magnitude and direction, and it's a push or a pull. And I brought this up earlier on in this lecture, but it's only become much more important recently. But it's very important with a force that we're specific about what this force is on and what is causing said force. So for a lot, you'll never do any harm by doing it. So I would recommend just being liberal with your labeling of forces. But when you can, if you think it's at all important, you should specify F on what, by what. Motion of an object is determined by the net force, right? So it doesn't matter how many forces are on an object. If they all add up to 0, then that object is not going to have any change in its motion. And the motion only changes if F net is, non-zero. What is the motion of an object? So what is momentum? When we say forces change the motion of an object, motion is described by its momentum. Momentum is also a vector quantity with a magnitude and a direction, and it's just its mass multiplied by its velocity. Velocity being yet another vector with a magnitude and a direction. It's how fast am I moving and what direction. So the reason we use this mass times velocity, not just the velocity, is because it gives us an idea what a force will do to like it describes like the inertia of an object, right? You'd be a lot more concerned with a bowling ball moving towards you at 5 miles an hour than you would with as a golf ball like moving towards you, right? Like something heavy carries a lot more inertia with it as something light. We'll see exactly what that means soon. I mean, we already should have, but soon in this review. But both mass and velocity are important in describing like what the motion of an object entails. And how do we change the momentum, like we said on the last slide, with a force? Not just a force, but a force over a time, right? If I apply a force for a longer amount of time, I impart more momentum to it, or we say impulse is just how much momentum we gave to something. It's an exchange of a momentum is impulse. So if I have some Fnet times delta t is my delta p, or my change in momentum. Applying a force over time changes momentum, and those are in the same direction. So if I apply a force to the north, my momentum changes to the north. That doesn't mean I have to be moving to the north, right? If I was moving south and I applied a force to the north, that might just slow me down, right? It could stop me and turn me around. We'll see a lot of this stuff later, but it's important to know that it just means my delta p. We need to know what my p initial was in order to know what's truly happening. More about momentum, you can still have momentum. You can still be moving even if Fnet is 0, right? It just can't, the momentum can't be changing. We have constant momentum if Fnet is 0. So I could just be moving 5 meters per second one way. This is not 5 meters per second, but if it was, that doesn't require a force. It only requires a force to change that. And we know that changing that can entail speeding up, slowing down, or even just changing the direction. When we deal with systems of objects, the total momentum in the system is just the sum of their momenta. Algebraically, we know that's adding up the components. Graphically, that would just mean summing one momentum arrow tip to tail with all the other momentum arrows. That's our total. And then for the entire system, we have these same momentum conservation rules that if Fnet on the system is 0, then the total momentum is conserved, or delta P total is 0. And if Fnet is not 0, so there is some external force acting on the system, then my P total is not conserved. In fact, it changes by exactly Fnet times delta T. Now, these are only true for everything in the system together, my P total. I can have no Fnet, but still have objects exchange momentum in between each other, right? In a collision, let's say I have two objects moving toward each other, that's our system. They collide and they bounce off each other, something like that. There's no external force, but clearly their individual momenta changed. Before they were moving one way, after they were moving the other. There's no net force. How do we reconcile that? Well, they just exchanged momentum, right? The change from one is equal and opposite the change from the other, and they add up to 0, which is what we see in this example here. I have a ball moving with some speed toward another ball that's stationary. It hits it and stops, and then the other one shoots off in the other direction. So if we use a momentum chart to kind of summarize what happens here, remember our momentum charts, we have columns for P initial, delta P, and P final, and rows for all the objects in our system plus the total. So ball 1 was moving forward, ball 2 was stationary, so our total is just the momentum of ball 1 to begin with. Our final state, we know ball 1 stopped and ball 2 was now moving to the right, and so our final momentum is just the momentum of ball 2. But since our delta P was 0, there's no net force, we know that the total initial and final momentum are the same, which tells us essentially that ball 1 transferred all of its momentum into ball 2. Our delta P column shows this most concisely, where if we look at the changes, ball 1 went from right to 0, so its change was just this vector flipped. Ball 2 went from 0 to this vector on the right, so its change was just that vector on the right. And these two delta P's, ball 1 and ball 2, add to 0. So they had equal and opposite impulses on each other, and so there's no net force required to change what their individual momenta are, so long as those exchanges all balance out to 0, as long as our ledger is consistent with the total being 0. So to just sum up all the things at play here. Like we were just, I'll go backwards on this slide. Forces applied over time cause a change in momentum in the same direction as that force. So if my force is this way, my change in momentum is the same way. What is momentum? It's mass times velocity. It describes not just how fast an object is moving and where, but its inertia. So if a very heavy object carries more momentum, it's harder to stop, it's harder to speed up. And then what is velocity? Well, it's change in position over change in time. We dealt a lot more with that this past week with kinematics, where we're actually looking at, okay, my object is traveling this fast, how far does it go, so on and so forth. But velocity is also a vector that just describes, here's my change in position from point A to point B. That's my vector. Divide that by time, and I get velocity. Final piece of this linear momentum force unit was elastic and inelastic collisions. There's really not that much meat to it here. If you really just want to memorize something super simple, all you need to know is that for inelastic collisions, kinetic energy is not conserved, and for elastic collisions, kinetic energy is conserved. So you can always just take all the objects in the system for the initial state, add up their 1/2 mv squared, so add up their kinetic energies, do the same thing for all of the objects in the final state. If those two things are equal, elastic. If those two things are not equal, inelastic. You can't go wrong doing it that way. There are some more interesting things beyond that, like if two things stick together, you know it has to be inelastic. Things cannot stick together without dissipating some energy or losing some kinetic energy. That's one thing to just keep in mind. If objects stick together, it is inelastic. Yeah.
So it's inelastic if the two objects don't have the same kinetic energy?
If the total is not the same. So if I have two objects, their total initial kinetic energy, so this kinetic energy plus this one, has to be the same as the total afterwards. So let's say two objects stick together, like they collide and stick together. If the new kinetic energy of that one combined object is not the same as the sum of the two in the initial state, then it's inelastic. And if it is the same, then it's elastic. Is there another question? Yep.
So I had a question about momentum on, I think it was practice quiz 4 or 5. You have like the momentum charts, you draw them. So I was confused a little bit on how exactly do you define a conserved system. So I know it's like if it's two things interacting directly, but I don't know what would make it not conserved.
Gotcha. Yeah. So so it's basically like, is there an F-net? So you want to look for what could be an F-net. Things that are often net forces may be friction, it also depends what you include in your system. So let's take an example of a ball being hit by a baseball bat. I could include just the ball in my system, in which case there is a net force, and that comes from the baseball bat. So that's an open system. Momentum is not conserved, right? Because there's this net force that causes a change in momentum. What if I include the baseball bat in my system? Now there's a ball and a bat, and now there's no net force, because the bat also, the change in momentum from the bat is also taken into account. So now whatever the momentum the ball got, that was my net change in momentum before, is now expressed as equal and opposite momentum lost from the bat, right? Or I could extend it even further. Why is the bat moving at all? Well, I have someone holding the bat. Maybe that's my external force that made the bat move, so on and so forth. So it really just depends where you draw the boundary for your system. Anything outside of that boundary is an external force or causing a net change in momentum. Anything within that boundary, so really anything that takes up a row in your momentum chart, is not an external force because it's included in here. I don't intend to give you an example where it's like very hazy where the boundary of your system should be. It's usually clearer like what an external force might be. Like in collision problems, I would probably include all the things that are colliding as rows in here. But if it's just like one object that gets blown by the wind or something, you probably want to make the wind an external force because we don't really care about what happens to the wind. right? If you don't care about what happens to something, probably don't want it taking up a row in your momentum chart, and it can just count as an external force. Did that help? Any other questions about momentum? Was I going to say anything else about elastic and inelastic? I don't think so. Yeah, and that's pretty much it. So just plug in and solve. I mean, you could memorize the things about them sticking together, but I'd say it's still probably always best to check. Oh, another thing I wanted to say. So kinetic energy is not conserved. Energy is still conserved. So that idea you have of like energy cannot be created or destroyed is still true. It just means it's dissipated to something else. So if we have an inelastic collision where it seems that energy disappeared, it didn't disappear. It just turned from kinetic energy into thermal energy or sound or any other form of things. But it's still there. It's just not kinetic anymore. Despite kinetic energy not being conserved, momentum is. That is, again, if there's no external force. The word conservation we kind of use a little bit imprecisely in this class. I prefer to think of it as that like energy and momentum are always conserved. It's just within a system it's only conserved if there's no external force, or energy is like kinetic energy is not conserved but total energy is. I don't know. The word conservation is kind of a tricky one to use precisely here. So I would just think of it in terms of if there's an external force, there's a change in momentum. If not, change in momentum is zero. And for kinetic energy, you can just evaluate it. And if it's the same initial and final, then it's elastic. And if not, inelastic.
So the part about the momentum being conserved in relation to like an external force or not, that's the same for like both of these scenarios?
Exactly, yeah. The kinetic energy piece and the momentum piece are like separate. So figuring out that a collision is elastic or inelastic doesn't tell us anything about the momentum. And it's helpful to use that in some problems because it gives us more information. So like if I was told that the collision is elastic, then that's just another equation I can write down, get rid of an unknown, something like that. But elasticity is completely separate from momentum conservation. And momentum conservation is always true, despite whether it's elastic or inelastic. All right, so again, no more linear momentum stuff for now. We're moving on to angular momentum and torques. So, just like we had velocity as a change in position over a change in time, the vector quantity, now we have an angular velocity, which is a change in angle over time. Instead of going from point A to point B, I go from angle A to angle B. And however quickly that happens is my angular velocity. And yes, all these things are vectors. We'll talk about how to identify the direction in a sec. Momentum was my velocity times my mass. Angular momentum is my angular velocity times we can use the word angular mass, but we call it rotational inertia. Rotational inertia, moment of inertia, but this I. And it's basically our rotational mass. Mass is how hard is it to change something's momentum, how hard is it to stop it, how hard is it to push it. Rotational inertia, or moment of inertia, is how hard is it to rotate it, how hard is it to stop it from rotating. Right? We'll talk about how to calculate it in a sec, but it just gives us a angular equivalent for mass. And then our angular momentum is that overarching description of the object's rotational motion. So not just how fast it's rotating and along what axis, but how much rotational inertia does it carry. Then finally, a change in momentum is brought about by a force over a time. A change in angular momentum is brought about by a net torque over time. So we'll talk about calculating torques, but applying a torque over some time gives us a change in angular momentum. So how do we do these directions? We use our right-hand rule. So again, for the right-hand rule, very important, take your right hand, especially if you're writing with your right hand, it can be annoying because it's natural to use the hand that's not occupied, but make sure it's your right because the left will give you the opposite answer, but you wrap your fingers in the direction of rotation, and then your thumb points in the direction that we're looking for. So for this disk that to us is rotating counterclockwise, we wrap our fingers, the direction of that rotation is up. Or if something was, like if we all look at this clock, it happens that we're all looking at it from a similar angle, so we could all just say the second hand is rotating clockwise, but if we want this to be true for everyone, and someone sitting like on the other side of the wall or something like that, we wrap our fingers with the direction of the spin, and our thumb points into the wall. So yeah, important to be able to do the right hand rule. If you're twisting your arm and going like this, there's probably an easier way to do it. But however you get it to work out, if your fingers are wrapping in that direction, your thumb will be pointing that way. Great, so yeah, good to practice that. And that's true for all of these quantities. So that's true if my angle, my delta theta is going from, like in this case, my arrow is going counterclockwise here. So a delta theta would be like the difference between this angle here and this angle there, right? Here's my delta theta sweeping counterclockwise, so I get this same up. Or for my omega, the direction of rotation is this way, so I get up. Or my angular momentum, the direction of it is that way, up. So delta theta, just like my change in position, my velocity, and my momentum are all in the same direction. My angle, my angular velocity, and my angular momentum are also all in the same direction. And then a torque provides a change in angular momentum in the same direction as that torque. So if my torque's out of the page, my delta L is out of the page. That doesn't mean my final L is going to be out of the page, right? It depends what my initial was. But my change from the torque is going to be in the direction of the torque. So let's go a little deeper into each of these. Angular velocity, like we said, theta is the angle, t is the amount of time. Units are radians for theta, so it's really unitless, but we're using pi here, so 2 pi is a complete circle, or 360 degrees. Pi over 2 is 90 degrees, etc. So in the little drawing I've done here, we wrap our fingers with our delta theta. Theta and omega both point out of the page. Angular momentum here, we add on our rotational inertia, just multiplies. To get angular momentum, we just multiply that I by angular velocity. And so if the angular velocity was out of the page, multiplying it by a scalar or something without a direction just also gives us out of the page. So theta, omega, and L all point out of the page here. How do we calculate this rotational inertia? The formula is this sum. So just that means you add up all the pieces, and you add up each piece's mass times its distance from your axis of rotation squared. So I is the sum of mr squared. So if we just have one, like if we're just spinning a ball on a rope, right, like circular motion, I'm spinning a ball on a rope over my head, its moment of inertia, or its rotational inertia, would just be the mass of that ball times the length of the rope, right? It's mass times its distance away. If I have 2 of those, then the total rotational inertia is just the sum of them. So the mass of one times this distance plus the mass of the other times its distance. A few times I use the example of like a dumbbell or something, right? And it does depend where my axis of rotation is, right? So here's my dumbbell. Each weight has a mass m, and we'll say it has a length L. If I rotate it about the center, then my moment of inertia is the sum of each mr squared. So if the whole thing is length L, each half is L over 2, right? So now my moment of inertia is m times L over 2 squared plus m times L over 2 squared. So each one of these would be L squared over 4, and we get m L squared over 2 for this setup. But if I decided to rotate it about one of the weights, so rotate it about the end point, then my I would just be m times L squared, right? Because this mass is a whole L away from my axis of rotation. And then this one would just be m times 0 squared, because this one is centered at the axis of rotation. So this one is ml squared. So same object, but the point that I used as my center of rotation changed what my rotational inertia is. And you saw that in DL, I think, when you had those bars with a weight on one side. It's a lot easier to rotate it about one side than the other, because the mass was concentrated in a certain spot. So if you hold it in a way that the mass is far away from your axis of rotation, it has a high rotational inertia and it's hard to rotate. But if you hold it right where the mass has no distance from where you're rotating it from, and so the rotational inertia is small and it's very easy to rotate. This is another thing where you need to know the concept, how it works, and be able to kind of argue and do very simple examples like this dumbbell, but I won't have you doing some crazy many-piece example where the real tricky part is just the math. I'm not trying to do that. Okay, so last piece we're missing is torque. How do we get these torques that cause a change in angular momentum? Well, we need a force, and it needs to be applied some distance away from our axis of rotation. So just like the rotational mass, it mattered not just the mass, but how far away it was. Same thing with the torque, or rotational force. It matters not only the force, but the distance away that it is from our axis of rotation. And not only that, but the angle, the direction that the force is applied. We see two examples here where we have the same force. One is applied perpendicularly to its position from the center, and the other is applied along that vector, like radially. And we know just experientially, if I apply a force perpendicularly like this, it will spin. This will create a torque. It will create a change in angular momentum of this wheel. But this example on the right, if I just pull on the edge of a bike wheel radially outward, nothing happens. It doesn't spin because there's no F perpendicular. So when we're finding torques, we need the force, and not just the force, but the perpendicular piece and its distance away from the center. And so how do we find that? Well, we need to use trig, and it's very similar to when we broke down forces into x and y components. In fact, this example that I'm showing up on the board here, F perpendicular and F parallel are just the y and x components, but sometimes that won't be the case, right? This could be at any angle, and we still just need two perpendicular components. So I know this is something that's really tricky, so it's really good to just practice examples of it. But in this case here, we have a wheel, and some force F is being applied some distance r away from the center at this angle. So if we want to find the torque that this force is going to create, we have the force, we have its distance away, so we just need to know what piece of this force is perpendicular to its position vector, to this r. And so the way we do that is, my favorite way to explain it is to, kind of break F down into two axes. The axis that is parallel to r, so just along, in this case, the x-axis, and the axis that is perpendicular to it, or in this case, the vertical y-axis. And that allows us to just break F down into these two perpendicular components. Using trig, we can see, based on this angle, perpendicular is F sine theta, and parallel would be cos theta, but we don't care about it. So it doesn't really matter there. But now, to find the torque, we just multiply r by our F perpendicular, which is F sine theta. That's not always true. Again, if I were to give you, or you find, based on how you solve this problem, the angle with respect to the vertical, then it would be FR cos theta. So you need to be very careful which trig function you use to find the component of F. Again, the one you're looking for is the one that is perpendicular to R. We also know that we can find R perpendicular instead of F perpendicular. So really what we're just looking for is the pieces of F and R that are perpendicular to each other. If they're already perpendicular, it's just F times R. That's my torque. But if they're not, we need F times R times some factor that decreases it. In this case, it's cos theta or sine theta, right? It's just, this is what they would be, F times R, if they were perpendicular, And then what that trig function serves to do is decrease that a bit, because these trig functions are always less than 1, right? And they're less than 1 by an amount that's dependent on this angle. But the further those are away from perpendicular, the smaller and smaller this will be. So that's what the trig function does. And you can kind of plug in some examples, or honestly just look up a video of like cosine or sine over time or something with something rotating around, like unit circle stuff. I don't know. We probably all saw it in high school, and it was very annoying then, and it's very annoying now, but we do need it. Anyway, if all we want is the piece of these two that is perpendicular, instead of finding f that's perpendicular to r, we could also equivalently find r that's perpendicular to f. So in this case, instead of extending r and finding the pieces of f that are parallel and perpendicular to it, I'm extending f, or using f as my basis, saying I'm going to use an axis that is parallel to f and perpendicular to it, and instead breaking r down into a parallel and a perpendicular component, in which case we only care about the perpendicular, and we get fr cos theta here. And those two things are equivalent. So if I were to find f perpendicular, I would still get this fr cos theta if this is my angle theta. Either one is equally valid. How do you pick between the two? Like, how do I decide whether I want to use f perpendicular or use r perpendicular? I prefer to just to not mess up the one that's already nice. And what that means is if f is already nicely in the y direction, or already nicely in the x direction, perfectly horizontal, then don't mess f up. Just use f, and then take r perpendicular. Because r is diagonal, let's just break it up into its x and y components, and then that will naturally give us the piece that's perpendicular to f. If r is already nice, if r is already nice, like this one, r is already horizontal. So let's not mess that up. R is already in the x direction. F is this weird diagonal, so let's just break f down into perpendicular and parallel. It's still not wrong to do it the other way. I just think it's easier because we're already used to dealing with x and y components. Questions about finding torque? Okay. Summary of angular momentum and torque, I pretty much just went through this all before, but just bringing back into what that torque finds us. So once we get this f perpendicular r, or fr perpendicular, that's our torque, and then we multiply it by a delta t, by a change in time, to get our change in angular momentum. So I do all this work to say what is the torque applied by this force, and then if I want to see how that affects an object's motion, I say, okay, how long is this torque applied for? That tells us what is the change in angular momentum caused by this torque over time, and then I can add that to the object's initial angular momentum. So if it was stopped, if it was just not rotating, it was 0, then whatever change in angular momentum is just its angular momentum. But if it had some initial, I need to add this delta to the initial to find out its final angular momentum. All right, that's all I have for angular momentum for today. Any questions? Yeah.
How do we use the right hand rule in order to find the in or out of the page?
It depends which way. I would phrase it as like, which way does this torque want the object to rotate? So like in these cases where we have static equilibrium, like we've been dealing with, or like you were dealing with a couple weeks ago. Like let's say we just had like a plank that's suspended by like a rope, right? We've worked with a problem like this a few times before, maybe just once, but this rope is applying some torque, or applying some force this way, so there's some tension force there, right? And then gravity is also pulling down on this plank here, so we have force of gravity, and we know that these two things apply torques, right? There's no rotation, so they add to 0, but there is some torque from each one of these. So which one is into the page and which one is out? Or even before that, just like what directions are these torques? We'll just isolate the force and say what direction does this force want the plank to rotate. So for the force of gravity, this force of gravity wants it to rotate clockwise, right? So I'll wrap my fingers around going clockwise, and that gives me force of gravity, gives a torque of gravity that is into the page. For the tension, which way does the tension want this plane to rotate? And it's counterclockwise, right? It's pulling it this way. So that gives me out of the page for the torque from tension. So just find whatever the force is, whatever the torque is, whichever way that force wants the thing to rotate, that's the direction you wrap your fingers to find the right-hand rule.
So as long as I use the right hand rule on and point it at which the tension is going.
You don't point your so when you do the right-hand rule, your thumb is your thumb is the result. So don't take your thumb and point it somewhere. What you're looking at, so you can even keep it tucked in. What you're looking at is curling your fingers, right? I want to curl my fingers with the rotation. So in this case, the torque or the tension is pulling this way, like left or counterclockwise. So that's the way I want to wrap my fingers. Then I flick my thumb out and I get out of the page. Same thing for gravity. I want my fingers to rotate downwards, so that's wrong. So they want to go this way, rotate clockwise. So that's how I flick my thumb out and get into the page. This might be difficult, but let's all visualize a car outside, so on the right, my right, your left of the classroom, driving toward the back of the room. So this is just like an exercise for all of us. There's a car driving toward the back of the room on this side. Which way, so it's moving this way forward, which way are its wheel, what is the direction of the angular velocity or angular momentum of the wheels? So try to use your right hand rule. The car is again outside to your left, moving toward the back of the room. What is the direction of the wheel's angular velocity and momentum? And this is an extra challenge to anyone who's watching this on YouTube right now. So the car is moving that way, which means its wheels are spinning like this, right? If I'm a car outside moving toward the back of the room, they're moving like this. So we wrap our fingers that way, and I get toward the right of the classroom. Your right, my left. So this way, toward the door.
Into the page.
Where's the page?
Sorry.
Yeah, so I mean, like,
Technically, if it wasn't. Sorry.
No, don't apologize. It's confusing, but yeah, like it could be into the page. If my page was over here, then yeah, it'd be into the page. If my page was here, it'd be out of the page. If my page was there, it'd be in the positive x direction or to the right.
Or it could be directly into us, the force.
Maybe the force, because the car is moving that way, so the force is that way, but the torque that this force produces, I would try to not think about forces so much as just which way is this going to rotate, and then wrap your fingers. Try to avoid pointing with forces. Okay, anything else about angular momentum? All right, let's move on, and we can go back to any of these after too. I'm almost done. I'll just do a quick review of the stuff we've been doing lately. Newton's laws, going back to forces, like linear forces, so no rotations here. A body at rest remains at rest, and a body in motion continues at a constant velocity along a straight line unless acted upon by external force. It's really just saying that if F net equals 0, then the motion of an object does not change. The motion meaning it doesn't slow down, it doesn't speed up, it doesn't turn either. Right? I could have constant speed, but if I turn, that means the direction changed. My velocity did change, and so I need a force. And that can be exemplified by something that's going around in a circle, right? It might be moving with a constant speed, however, the direction of that speed is always changing. And so it does not have a constant velocity because the direction is always changing. And like we saw, that actually does require a force. To have something going in a circle, there always needs to be this force that's pointing toward the center or perpendicular to its motion that keeps it going on a circular path. You also were not quizzed on circular motion stuff, so that could be a good thing to review. Second law, the total force on a body gives it acceleration, which is in the direction of the force. That's just F net equals ma. So if I apply a force to something, the motion that results will be some acceleration that is related to the force based on the mass. So if an object of certain mass accelerates some amount, I need this F net to cause that. Those were two very unclear ways of saying that, but F equals ma, right? If I have an object that accelerates, I know the force that I needed to do that was m times a. And then finally, every action has an equal opposite reaction, or the way it's put here, that if one object exerts a force on another, the other exerts an equal and opposite force back. So a concise way of saying that, I have two objects, A and B. If there's one force on A by B, so B exerts a force on A, then there will have to be another force on B by A. So A exerts an equal and opposite force on B. That does not mean that those two things cancel, right? I would never add just F on B by A plus F on A by B up together to get 0, because one's on B and one is on A. So it wouldn't make sense to add them together and get 0. They still do produce two different accelerations in those two different objects because they're acting on separate things. We just have Newton's third law to say that both of them should exist. If one exists, the other must equal and opposite to it. So in a simple example here where there's just a person pushing a box along a floor, we're going to look at the forces on the box. In the y direction, it's a good example of our first law, which is that there's no net force. Gravity and normal force completely cancel out. And so if F net is 0, then the acceleration in the y direction is 0. And our initial velocity was 0, so there's just no change. It stays still in the y direction. The second law is very clearly seen in the x direction, where we do have a net force. The person is pushing the box to the right. There still is some friction, so the force on the box by the floor going the opposite way, but the person is pushing harder than the friction. So the person wins, and the box does slide. The box has some net force to the right, and it does accelerate. How much? Well, it's exactly the net force divided by the mass, or in other words, the net force is the mass times its acceleration, the push and the friction in opposite ways. But yeah, we need the mass and the net force to tell us about what the acceleration of the box is. We could still apply these laws to the other directions. So the first law applied to the x direction, it's like the object in motion stays in motion unless acted upon by an outside force. Well, this one is acted upon by an outside force, so that's why its motion changes. Second law in the y direction, F equals ma, F is 0, so A is 0 in the y direction. Okay, so now plotting these out. This is going into kinematics, which is really just like how do we relate acceleration, velocity, and position, just figuring out the motion of an object over time based on the forces that are applied on it. So there's a lot of math here, but the key equations that we want really are these two: the position of an object over time and the velocity of an object over time. But maybe before we get into these, let's do the qualitative side of things here. So the picture we have, and I know I just explained this in lecture, but I think it's a really good example to go over again. We have a ball, and it is falling down with some velocity to the right. So it's moving to the right, and it's being pulled directly down by gravity. So let's plot out just its motion in the y direction. And for the y, we know x and y act completely separately, so the fact that this ball has some velocity in the x direction is irrelevant, right? We know it has some initial velocity that's down and to the right, so the piece of the initial velocity we care about is only the piece that's pointing down. Also, our net force is only due to gravity, right? Despite the fact that it has some initial velocity, whatever that is, the net force is just gravity pulling down. And so its change from this initial velocity will only be due to gravity. So first, let's start with acceleration. The acceleration is, again, only due to gravity, and gravity doesn't change over time, so its acceleration is always just negative g, or negative 10 meters per second squared. So this means that from the time I drop it, every second its velocity will decrease by 10 meters per second. And that, even though I said decrease, it's really speeding up. It's just speeding up downward, right? It starts at, not 0, but it starts at the y component of v naught, which is pointing down, and then after 1 second, add 10 meters per second to that. After 2 seconds, add 10 meters per second to that. So, but constant acceleration. And then what I just started to describe with the velocity, my initial velocity before gravity starts pulling on it, or just as it's starting, is just my y component of v naught. So that's just vy, some negative number that's, well, negative. Then as gravity acts on this ball, it speeds it up over time in the downward direction. So keep subtracting away from the velocity. And the relationship between this velocity and this acceleration is that the acceleration is the slope, the rate of change of the velocity. So my acceleration is constant and negative, and so my slope of my velocity is constant and negative. Over time, it decreases at a constant rate. So this negative 10 meters per second squared is the rise over run. Every second, this decreases by 10 meters per second. Right? So that's how we get this velocity over time. Over time, the ball is falling faster and faster and faster. Then to go a step further than that, let's find its position over time. If we say it starts at position 0 and falls down, the position becomes more and more negative. We also know that over time, it speeds up. Right? So it not only becomes more and more negative, but it becomes negative faster. It's moving faster here toward the right at a later time than it is at an earlier time, which is why the slope of the position increases, right? At first it's falling, it's becoming lower and lower, falling down at a slower rate, and then as it speeds up in the downward direction, it falls faster and faster and faster, and this line becomes steeper. So velocity is the rate of change of the position graph. So at each point along here, the slope is demonstrated by the velocity. So if my velocity here is negative 15 meters per second, then up here, the slope at that time is negative 15 meters per second. And the units work out, right? Because the slope is rise over run. The rise is meters. The run is seconds. So meters per second. So going from top to bottom, it's my position, take a derivative of that, or really just what is the rate of change of this, the slope of this over time. That's my velocity. So going from like a parabola, or like something that has a y squared in it, to a line, which is just something that has a y in it, or like a t, really is the time is the independent variable. And then going from a line, what's the slope of that? Well, that's constant, so that's just a flat line. To see that mathematically, that's where we get these equations here. The acceleration, the equation for that is very simple. It's just a equals negative 10 meters per second squared. And you won't, like I said in lecture, you won't have to do anything more complicated than that for acceleration, or at least not like a function. So if something has a changing acceleration, you won't have to say like, my acceleration over time does something like this, or like curves or something like that. If there's a change in acceleration, it will just be like, it's 0 here, and then it's this here, and then it's this here, something like that. Right? So your acceleration will always be just constant values over some interval. And as a result, your velocity will always be some series of like straight lines. Right? Your velocity will never have a curve in it. And then as a result, your position can have a curve. But the position is the only graph that curves. So I'm saying a lot of kind of general stuff here. This is all really like calculus concept, but you're not responsible for that, and I wouldn't think of it as like calculus. It's just can be helpful to view things as, knowing that one thing is the slope of the other, or really the rate of change. It is important that you know what a rate of change is. This is how fast this is changing. This is how fast this is changing. So anyway, these equations, my plot of y, you can see, is a curve. It's actually a piece of a parabola. And this equation for what y is the equation for a parabola, right? You have like ax squared plus bx plus c. If that recalls something, equals y, something from high school or calculus in college, something like that. But it gives us a parabola, and these things can be positive or negative or bigger or smaller, and that what determines whether the parabola, where it starts, like in the vertical direction, or if it's shifted left or shifted right, or if it's wider or narrower, or pointing up or pointing down. All those things can change, but it is a parabola, which is basically like a thing with t squared, t, and a constant. So what are these terms? Well, so the thing we're finding is y, or y final. That's just what is my position at any given time. And that's equal to the sum of these three things. First, it's my initial position. That definitely matters, right? I want to know where, if I want to know where I end up, I need to know where I started. So I take my starting position and then add to it my initial velocity in the y direction times time. So was I moving to begin with? That also affects where I end up, right? If I apply some force to myself and I want to know where I end up, it matters if I started at a standstill or if I started moving in the same direction as the force or moving against it, something like that. So I add to that velocity times time, which gives me a translation, right? Meters per second times seconds gives me an amount of meters that I traveled as a result of my initial velocity. And then the final term is the acceleration piece. The reason it's 1/2 at squared is, well, you can think the units have to work out, right? Acceleration is meters per second squared, so I better multiply it by seconds squared. The 1/2 just comes in because calculus, like if you integrate, you get the 1/2. Doesn't really matter. Just accept that there's a 1/2 there. Maybe here's an intuitive way to understand it. Like I said before, when I'm accelerating due to gravity, so let's say I have a ball and I drop it, and it starts at 0 velocity and then speeds up as it falls. We know due to that negative 10 meters per second squared acceleration that after 1 second, its velocity will be negative 10 meters per second, right? Every second, it increases or decreases its velocity by 10 meters per second. So it started at 0 velocity and got to negative 10 meters per second. However, it has not traveled 10 meters in that amount of time. Even though its velocity is now 10 meters per second, and it's been 1 second, it had to speed up from 0 to 10 meters per second, or negative 10 meters per second, over that amount of time. So it took that whole second to get there. Initially, it started at 0. Halfway through, it was somewhere around like 5 meters per second, not exactly, but something like that. But it had to speed up. So even though it got to 10 meters per second, it was moving less than 10 meters per second before that. So it didn't get to travel the whole 10 meters. And that's why we need this 1/2 factor. If that helped, great. If not, doesn't really matter. There's just a 1/2 there. But what this term tells us is how the position changes as a result of acceleration, right? I have this ball, starts at y equals 0, so my initial y is 0. It has some initial downward velocity. That's my vy0 times t, so that multiplied that initial downward velocity times time to see how far it traveled down. But then I also need this term that tells us how much did this ball get pulled down due to gravity. So it would be 1/2 times negative 10 meters per second times whatever time squared. So initial condition, acceleration that occurred due to a net force. And that's how we get the position at any point. So I could apply this to any point along here. I want how far did I travel after 5 seconds. So I plug in 0, I plug in assuming I know what my initial velocity was, times 5 seconds, times 1/2 times negative 10 meters per second squared, times 5 seconds squared. I just plug in, I get an answer for my y as a function of t. So this plotted for this example gives me that. For my velocity over time, it's a little bit simpler. It's just my velocity at any given point, my v final for the time that I'm looking for is just my v initial plus acceleration times time. That's the more simple case I was saying, where like every second gravity subtracts 10 meters per second from the velocity. So that would be here. A is negative 10 times time. So every second we get an additional minus 10 off of our initial velocity. And that produces a line. right? This looks a lot like y equals mx plus b. The AT piece is our mx, that's just our slope, times our time. That tells us how far down the curve we've gone. And my y initial, or my vy initial, is just where does this curve start. If I started at a standstill, it would go through the origin and go down. If I started with a positive velocity, it would start up here, moving forward, and then moving upward, and then turn around and start falling. But in this case, it starts moving downward and just speeds up. And like I said, you're only going to see, at least piecewise, constant acceleration. And so acceleration will just be a series of values. -10, 0, +10, whatever, depending on what the force is. This example in the x direction is a lot simpler. So we remember our v initial has a downward and a right component here. So the negative y direction, we already did the y direction. Let's look at the x. In that case, we just have an initial velocity in the x direction. That's just the x component of this v0, and no acceleration, right? Gravity only acts downward, and so in the x direction, there is no acceleration. No net force, so no acceleration. That means our velocity is constant. Or if we want to see that in this equation here, if I want my v final, I'll just take my v initial, which is whatever it was, that initial velocity moving to the right, plus acceleration times time. Acceleration is 0. So my velocity is always just my initial value. And then my position simplifies because this acceleration again is 0. So I just get my initial position plus my initial velocity times time. It's just where did I start? And then how fast am I moving times time. And that is the equation of a line. So with constant velocity, our position just looks like a line, which makes sense, right? An object is moving to the right, so over time, with a constant speed, so over time its position just increases at a constant rate. The slope is constant. And what is that slope? It's exactly the value of this velocity. This equation has been floating around too, and it will be on your equation sheet. I don't intend to use it. It's just some relationship between the change in velocity and the change in position without this time component to it. I don't know, I just don't think it's particularly, I mean, it can be useful, but for the purposes of learning in this course, it's just derived from kinetic energy conservation, and it's like, I don't know, I just don't think it's helpful to give you another equation that doesn't have a lot of conceptual weight to it. All right, so finally, just an example that initial conditions are important in this case. So let's say I have this box that is being pushed to the left, and we want to plot out its motion. So the net force is to the left, so its net acceleration is negative. It's just this constant force. So we have this constant negative acceleration. But if we want to plot its velocity over time, it depends what the initial velocity was, right? So if my initial velocity was 0, and I have constant negative acceleration, I start at 0, and then I just stopped, then start moving backwards at an increasingly fast rate. If my initial velocity is to the right, but then I'm accelerating to the left, that means I'm moving to the right, but then I start slowing down because I'm subtracting away velocity, and then eventually I'll reach a stop, which is when this gets to 0, but then I'm still accelerating negative, so now if I subtract from 0, I turn around and I start speeding up in the negative direction. If I was already moving left, then like the previous example, and then I apply an acceleration in that direction, I'll just speed up from the get-go. So all of these lines here for my velocity have the same slope, but the behavior of the object really depends on what direction it is traveling to start with. And below here are just the position plots that correlate to each one of these velocity charts, where if it was stopped and then applied the force, we're at 0 and then moved backwards increasingly quickly. If we were moving to the right and then applied the force to the left, we are moving forward. So this is increasing my x coordinate, moving forward, but then slows down and stops. So now the slope is 0. We're still in the positive x area, but we turn around. So now we start going back the other way, back towards 0, and then accelerate in the negative direction. And if we were initially moving left, same thing. We still start at 0, but now we move backwards a lot quicker because we started with a negative velocity and make that even more negative right away. So this piece here is just like, well, I guess all of these are chunks of the same parabola, right? So this piece here is just starting here when it stopped and moving down, right? This piece here is starting somewhere over here when it was already moving backwards and moving down. All of these, the shape of this parabola is described by the acceleration. The velocity and position just describe where we plop it down on here. Questions? That's the end of what I have for slides prepared. We have a few